Okay, let's go ahead and talk about graphs. I apologize for everyone on the internet because I'm going to draw a picture and it makes perfect sense. So far we've talked about trees. You know, you have a node, you have a root goes down to here, maybe it has another child over here. We've got some fancy trees that can have more than two. Maybe this guy goes over here, this one goes down over here, maybe this one has a child over here. All right, you ready for this? A graph is like a tree, except you can go back. Got it? That's a graph. So people online, it's like a tree, except for now any node can point to any other node, which means it's no longer a tree. Also, that makes it interesting. Are all trees graphs?
I guess so.
Yeah. So all trees are graphs. So you've actually been using a graph the whole time, just a very specific version of it. But we're going to talk about a general purpose graph today, and this has application all over the place. Google Maps uses a graph, for example. All right, we'll learn about graphs, basic terminology. These slides are old because I used the new ones and it started using Korean letters. So we'll just use the old slides. The material didn't change. All right, yeah, we're going to do that. Great. Okay. Can anyone pronounce that? I could try, but I'm just going to slaughter it. So I'm just going to call it the bridge problem. The river of, oh man, I think it's Prattle, hopefully, flows around the island of that and then divides into two branches. So the question is, can you make a path such that you cross every bridge exactly once? You can start wherever you want, you can end wherever you want, but is there a path that you can take that goes over every bridge exactly once?
Yeah.
Okay, what's the path?
You could start between D, E, and G, and then just go around.
Which ones are B?
So the bridges D, E, and G.
D, E, G, all right.
And then go through D, C, A, B.
Well, then you just went through D again. Right.
So you start in.
Good morning.
Good morning. Start here, right?
In the water?
Yeah, in the water. Can you not start in the water?
How would you start? No, you gotta start on land.
Oh, start on land.
Yeah, no starting in water.
Go over the bridge.
Oh. I thought it was going under them.
That is interesting, going under the bridge. I didn't think of that. Good thinking outside the box. No, you have to start on land. And you have to stay on land, no going through water. So for those that just came in, you can't go in water, and these are bridges. So the little letters are bridges. Bridge C, D, A, B, E, little g, and little f. Is there a path? You can start wherever you want, end wherever you want, but is there a path where you cross every bridge exactly once?
Yeah.
You say yes, and we have a no. Okay. Well, if you say yes, what is it?
G, E, D, C.
G, E,
B,
B,
A, C.
C.
Is there one left?
You got F and D.
Well, does the river continue? The river doesn't just stop.
Yeah, we'll just
right?
say the river goes ad infinitum.
You can't just walk around the river.
And you can't jump or fly. And we don't have boat cars. You say no. Why no?
I haven't figured out the final proof, but any place you start, you're going to, because of the way the two islands and two shores are, you're going to end up with a bridge you've crossed in between you and the bridge you need to.
Okay. Any other guesses? He's looking really intently. Still looking?
Yeah.
All right. So, in 1736, and that's pronounced Euler. I got that one, even though there's no O in it, but that's okay. Or I. Euler represented the problem as a graph and answered the question no. Well, that's unfortunate. All right. Over the past 200 years, so that'd be from 1736 to 1936. We're coming up on 300 here, slides. Update your slides. Wow. Man, how old are you? Did PowerPoint exist in 1936? I don't think so. All right. Graph theory has been applied to a variety of problems: electrical circuits, compound, highway maps, analysis, finding shortest route. Yes, so Google Maps uses graphs. And actually, we're going to go through Dijkstra's algorithm today, which is the basis of what Google Maps uses, although they, of course, use a very optimized, modified version. But at least you'll get an idea of what they do. Linguistic, genetics, social. Okay, this is used all over the place. A lot. But, of course, we got to have a bunch of definitions. How many of y'all have taken discrete math?
We're taking,
it.
3 of us are taking it.
All right, maybe let me rephrase the question. Is anyone not taking discrete math or not currently in it? Excellent. Good. This notation, it makes perfect sense. Those of you online, well, I'll try and help you out. A is an element of X. Okay, that's great. Subset, Y. Okay, great. Intersection and union. Yeah, the other slides, they put Korean letters for all these. It was really difficult to see. All right, so we got element, subset, intersection, union. All right, we're good. So that's the cross. A cross B is a set of all ordered pairs of elements A and B. So A and B in here are sets, aka multiple numbers. So when you cross them, you get one element. The combination of all of them is the bar or the cross. So a graph is just a collection of vertices and edges. The slides call them vertices. I will sometimes call them nodes. Just note that vertice and node are interchangeable here. I've been using node the whole time. The slides call them vertices. Officially in the literature, they're called vertices. They're nodes. So I'm going to call them nodes a lot. Just know that that means vertice. Good. V is a finite non-empty set of vertices. So a graph has to have at least one node, aka one location. If it helps a lot, you could think of this as flight plans. You know, another very popular one is these are the different cities you can fly to, and the arrows are which ones you can go to. E is a subset of all the possible edges between the vertices. So this part may seem a little confusing, but it does make sense to saying that the edges, the size of or the number of edges is limited by the number of nodes or vertices that you have. Elements in E are pairs of elements of nodes. E are called edges. All right, great. So yes, a graph is just a collection of nodes and edges. Great. A directed graph or a digraph, they're ordered pairs. Undirected, they're not. Here, let me show you what that means. This is a directed graph. Why? Because you explicitly have an arrow going from here to here. An undirected graph would mean that every connection goes both directions. Now, normally a directed graph is what's used for various reasons. The slide is going to use both, but just know that when you're in a directed graph, you can have one edge going from here to here and another edge going back like that. Perfectly fine. So this is the directed drawing. The undirected drawing will either have the arrow pointing both ways or no arrow. If there's no arrow, it's undirected, meaning that you can go both directions. This was
Undirected.
oh, perfect. Just making sure everyone's paying attention. Subgraph, okay. You can look at the notation, aka you just draw a circle around part of the graph, and that's your subgraph. Any edges coming out, you ignore. Hey, here's some graphs. Undirected graphs. Here are some directed graphs. So, is there a way to go from 2 to 4? Oh, I'm sorry, on this one. Whew, let's start there.
On G1.
On G1. Whew.
There is a way. Wait.
Nope.
No.
Everything flows down and right. This can represent like a pipe system where you're starting here and sewage is going somewhere. This would be more like an airport. So can you go from 0 to 8?
Zero, 1, 5, 4, 8.
0, 1, 5, 4, 8. Is there another way to 8?
0, 3, 4, 8.
Yep. You ready? There's even another way. And y'all are going to roll your eyes. Here we go. 0, 3, 6, 0, 1, 5, 4, 8. Ha-ha!
And there's another one.
And there's another one. Yes. You can keep doing this loop, or you can go and do this loop as many times as you want. So there really are ad infinitum a number of paths to get from 0 to 8 of varying length. Yeah. But then once you're at 7, you're kind of stuck. Yeah. Although you're at 8, you can get out and do what you want. Yeah, 7's the dead end here. Wow. Don't go there. All right. They love to give even more definitions. Adjacent means there's an edge from one vertex to the other. There has to be a direct edge. So, back to G2. Good morning. Are 1 to 5, actually, is the way to put it. Are they adjacent? 1 to 5? But is 1 to 4 adjacent? No, it's not adjacent, but there does exist a path from 1 to 4, but 1 to 4 is not adjacent. And I'm saying 2 to emphasize that this is directed, so yeah, you have to specify the direction. All right, incident, if edge, then E is an instant, sure, I don't care. I'm not going to use that word. Parallel edges, yeah, it's nice. A simple graph has no loops or parallel edges. Yeah, so G1 is simple because there's no loops and there's no parallel edges, so we're fine, great. All right, I talked about a path. Sequence of nodes or vertices such that when you follow them, there's an edge that links from one to the other, great. Connected vertices, there's a path, simple path, which all vertices except possibly the first and last are distinct. So there are a limited number of simple paths from 0 to 8, because you can go 0, 3, 4, 8, was 0, 1, 5, 4, 8. But if I try to do 0, 3, 6, and back to 0, that's no longer simple because I'm revisiting the same path. Are there only 2? There might only be 2. Yeah. A cycle is known as a loop. Oh my goodness. Connected means that a path exists from one vertex to another. Strongly connected, any two vertices of the graph are connected. And then there's fully connected, or we won't go there. Fully connected, basically, fully connected means that there's an edge from every vertex to every other vertex. So it's a complete graph or a fully connected graph. Yeah, so connected just means that there always exists a path. Strongly connected means that all the vertices are connected, and then fully connected means that, it means there's always an edge from one vertex to another. Whew. You don't need to know all these, so I don't really know why they tell you these. All right. How do we represent a graph? Okay, how are we going to do it?
With arrows and nodes.
Arrows and nodes. Okay. Well, how would you know where to search? Usually, I mean, with the tree, you had your starting node because you always had your root. I mean, in this graph over here, if you started at 7, how would you get anywhere?
You wouldn't.
You wouldn't. And you can't really know which one is the root node because there may not be a root node. Also, we haven't really drawn this, but that's a graph. This whole thing is a graph. It has two disjointed subgraphs, but the whole thing is still a graph. So even if you pick a root and you picked a good root, there's no way to get to these nodes over here. So you can't just have nodes and vertices and just plop them down like a binary tree because there's no way to get to all the nodes. Oh, that's unfortunate.
Take a set of vertices and a set of edges. You can store them in like an array or linked list or whatever you want.
Okay, you're going the right way. So the first way we're going to do it, I think, is simpler to understand, although it is not the way that most people represent a graph, and that reason should become obvious fairly quick. But let's go ahead and give these things numbers. We got 0, 1, 2, 3, 4, 5, and 6. I don't want to erase the stay positives, but it really is in the way. Okay. The first way is with an adjacency matrix. So the matrix is n by n, where n is the number of nodes or vertices. So we'll have 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6.
That's huge.
Yeah, that's correct. It's also really annoying to draw this matrix. Okay. And what do you fill in? You fill in the if they're connected or not. Now, I'm going to skip ahead. If you're going to do that, when you do this in algorithms, you're going to have the identity matrix, or I forgot what the matrix is called, which just fills in ones and zeros if they're connected. That is somewhat helpful, but for what we're doing today, it's more helpful to actually store what the weight of the edge is. And in general, not always, but in general, the edges are what carry a weight. When I say that, I mean to go from 0 to 1 may take 45 minutes. Going from 1 to 0, we'll say it takes 35 minutes for some magical reason. Going from 1 to 2 takes 100 minutes. Going from 2 back to 0, we'll say it takes 90 minutes. Going from 4 to, I say minutes, we're airplanes, this is an airport or something, whatever. 4 to 30, someone give me a number.
42.
Nice. How about 3 to 5?
Also 42.
Okay. And, oh, I didn't give a direction here. Are we going from 3 to 6 or 6 to 3?
Both ways.
Oh, nice. So we'll have going one here, and then we'll have one going back. From 3 to 6 is how much?
3's charm.
Which one?
42.
42. And just to be different, we'll say from 6 to 3 is 43. Oh,
Oof.
oh, whew, rough. Whew. Okay. So when you have this matrix, you fill in what the weight of all the edges are, and this will represent your entire graph. So how much time does it take to go from 0 to 0?
Hopefully 0.
Yeah, good. I really hope so. Now this is the weight of not the path, but the edge. So from 0 to 1, okay, we have a number. That is
45.
40. Yep. How about 0 to 2? There is not an edge, so we don't say the path. We put in something to represent infinity, whatever you choose. 0 to 3. 0 to 4. 0 to 5. 0 to 6. Oh, I didn't hear you that time. All right, how about from 1 to 0?
35.
1 to 1? All right, I'm going to cheat.
Oof.
Oh, everyone got that?
Yeah.
Good. 1 to 2. 1 to 3? Okay, these are all. All right, 2 to 0. 90. Poor people online. 2 to 1.
You should take a picture.
Let's see. What are we, 2 to 3? Oh yeah, we can't do anything. How about 3 to 0? In fact, all these are going to be not connected because they can't go to the first part of the graph.
Wouldn't we just use -1?
Unless we have airplanes that go across date lines and then are hypersonic, and then you can arrive before you left. Anyways. There are situations where it could become negative, so I'm just using infinite just to, I mean, I could put unhappy face, right? You just need to signify there's no connection, is what you gotta do. Where are we? Oh yeah, 3 to 4. How about 3 to 5? And 3 to 6? All right, how about 4 to 3? Nothing. What are we, 5 to 3?
No connection.
Oh wow, once you're at 5, it's the dead
4 or
zone.
5.
What's that?
4 or 5.
Yeah, no. Eek. 6 to 3. All right. Okay. So hopefully it's obvious what the problem is.
Yeah.
What's the problem?
It's ginormous.
It's ginormous, and you're wasting a lot of space by signifying no connection. But what's the big O to find the weight of an edge between two vertices?
1.
1. That's the biggest advantage here, is that the big O to find a vertex is always going to be 1. We're going to start off with this one today because hopefully that's straightforward. It's easy to see. Okay. All right. All right then. I failed. All right. Let's see, hold on. JC matrix, so they're showing it as 0 or 1 if these verge an edge, 0 otherwise. I replace that with the weight of the edge because that's where things actually become useful. All right, any questions, comments, screams?
This is nowhere near as intimidating as Project 4.
The only thing I can do.
Yeah, Project 4 is just, well, I don't know. Which one's more intimidating, Project 1 or 4? Because 4 is obviously a harder project, but I give you 1 right off the bat.
I think if I had been like more prepared for Project 1, Project 4 is more intimidating.
Right.
Like,
That's what I'm saying. Which one? Because I'm assuming now you look at Project 1 and you go, oh, hopefully.
Yeah.
Hopefully is what happens. But yes, okay. All right. Let's jump over. I'll pause the recording and then we'll go some.